You may want to pay a little closer attention to this one. Let's read it. F of x equals to 3x to the fifth minus 7x to the third plus 9x. And all that's divided by 11x to the seventh plus x cubed minus 13x. Now I've deliberately put odd numbers all through the thing. All the exponents are odd. All the coefficients are odd. One thing about coefficients are the numbers multiplying the variable parts of terms. The coefficients make absolutely no difference as far as even and odd functions. They have no influence whatsoever. The one thing that determines whether you have an even or odd function are the exponents. And it is true that normally if you have odd exponents, then you probably have an odd function. And even exponents normally give you an even function. But this is an exception to that rule. This is actually an even function. So let's go through it. If my test for even or odd functions is to replace x with negative x. And so when we do that, we'll plug all that in, and we get 3 times negative x to the fifth power minus 7 x negative x cubed plus 9 times negative x. And all this is divided by 11 times negative x to the seventh plus negative x to the third minus 13 times negative x. Okay, so let's go through all this stuff. And each of these powers will give us a negative. For example, negative x to the fifth is negative x to the fifth. Okay, because we have an odd power. So this term becomes minus 3 x to the fifth. This one is negative x cubed times negative 7, so I have a plus 7x to the third. Here I've got minus 9x. And all the way down the line here, let's see, negative 11x to the seventh minus x cubed plus 13x. All right. Now, our test to see for even functions is this equal to the original function? And it is, because if you factor out a negative, in fact, I'm going to factor out as a negative 1. Out of the numerator, I've got 3x to the fifth minus 7x cubed plus 9x. And if I factor a negative 1 from the denominator, that gives us 11x to the seventh plus x cubed minus 13x. Now look what happens. The two negatives cancel. And what we're left with, if you look, is the original function. So this turns out to be an even function because it satisfied the test that f of negative x equals to f of x. In other words, change of the input does not change the output. So this is an even function. All right, so there we go. A little tricky example there. But all right, well, I'm going to erase the board and then let's talk about odd functions. And then when we're done with that, then we'll look at examples of functions that are neither even nor odd. Because actually, when you think about it, most functions don't satisfy either of those symmetry properties that apply to even and odd functions. And so it really is a special case. Now, here's our example of an odd function. F of x equals x cubed minus 4x. Now here's, again, you'll have to take my word for it. We'll analyze these in more depth in another chapter. But here's what this one looks like. It crosses the x-axis in 3 places at negative 2, 0, and positive 2. And you've seen this shape before. This is the cubic polynomial shape. And there we go. So what is an odd function? An odd function is one which is symmetric to the origin. And remember what point symmetry means. If it's symmetric to a point, then I can rotate it around that point 180 degrees and end up with the same thing. So here, if I took the right half, rotated 180 degrees, I would have the left half. Same if you took the left half and rotated it around. So 180 degree rotational symmetry, that's what point symmetry is. And in fact, this one is also symmetric to the origin. And so that quality makes it an odd function. So let's write that up. Odd functions are symmetric to the origin. Okay, point symmetry to the origin. All right, well, now what is the algebraic property of such a function? And one thing you might notice is that this graph, and in fact you'll find this with all of them, there are repetitions of this shape in the first quadrant down in the third quadrant. And this second quadrant shape is inverted and rotated to the, I'm sorry, this fourth quadrant is inverted and rotated to the second quadrant. So there's a sort of this opposite quadrant thing going on. And for example, let's plug a number in. And how about 1? So if I put 1 into here, f at 1 would be 1 minus 4 is negative 3. So it's about here. This is 1, negative 3. And where is f of negative 1? And, you know, I didn't draw this quite right. I know the bottom of the graph is not at negative 1. But this is a little bit skewed because I didn't draw it perfectly. The top of the graph is not at negative 1 either. It's not exactly in between these numbers. It's actually off by like square root of 3 or something. But anyway, if we drew this completely accurately, you would find that this point corresponds to that point by this rotational symmetry. Here, this point would rotate 180 degrees from 2 to minus 2. And so, but in this case, this negative becomes a positive. And so if you think about it, this is a little more complicated, I think, than the the symmetry of the even functions, which are symmetric to the line. But it works out this way, that the test for odd functions is this. If I like to print rather than do cursive,